Okay, let's talk about decomposition reactions. So a decomposition reaction is one where you have one compound that breaks down into two or more substances. So those substances could be just individual elements, okay? So the compound completely breaks apart into elements. So I've got a couple examples here. If we have gold 3 fluoride and it decomposed into the elements, we would get gold and we would get fluorine, okay? If we had aluminum oxide and it broke down completely into elements, you would get aluminum and oxygen, okay? But if you're just given the compound and you need to predict the products of this decomposition reaction, you do also need to be able to determine, other than splitting it up into elements, you need to know, is that element a monatomic element or is it a diatomic or something else? Okay, and all metals are monatomic, meaning if it's an ionic compound splitting apart into elements, then the metal is always just going to be that metal, one of them, one atom of it. And if you need more than one to balance the equation, you'd put a coefficient, but you shouldn't have a subscript on those ever. And they should be in the solid phase, unless if you have mercury. And then the non-metal portion, you know, may be monatomic, it may be diatomic, it may be polyatomic. You should at least know, like, noble gases, those things are monatomic always. Now, those won't come up in a decomposition reaction, or most of the time they wouldn't, because most of the time they're not part of a compound. But if they were, they would come apart and only be one atom of it. Whereas you have your diatomics, your hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine, and iodine. All of those things should have a subscript of 2 with them, okay? And the phase is going to be just depending on which one it is. You can always look that up if you don't know, or if it's not told to you already. Let's see. Once you figure out the products, you balance the reaction by putting coefficients. And so the reactions I've given, I've got, you know, subscripts when something needs a subscript based on the compound, and I have coefficients indicating when I need more than one to balance the reaction. But those reactions given there are complete decompositions. So the compound's completely breaking up into the elements. Now, I did give examples where it was ionic compounds breaking up. It could be a covalent compound decomposing into the elements as well. You can also have decompositions that just decompose a compound into simpler compounds. So not completely into each individual element, but they give, you know, just smaller molecules. And so a couple examples, if you have calcium carbonate, it's going to break up into calcium oxide and carbon dioxide. Or if you have calcium sulfate dihydrate, it's going to break up into calcium sulfate and water. And so those are much harder to just predict the products if you're not given any kind of hint about what would happen. So most of the time, if someone talks about a decomposition, if they don't tell you products, they're probably talking about a complete decomposition into the elements. If it's an incomplete decomposition, so what those others would be, where you get just smaller molecules, usually you'd be told what you get. But there's different resources that'll tell you kind of some general information about what things tend to decompose into. And I've got a table here that gives you some information. Well, when you have oxides and halides of metals, generally they're going to break down completely into the metal and the oxide and oxygen, or the metal and the halogen, okay? I mean, that's going to be true really for any compound that's just 2 elements. If it decomposes, it has to decompose into the elements. Whereas if you have peroxides, those are going to form oxygen gas and then have some oxide remaining. If you have a metal carbonate, carbonates tend to form carbon dioxide, and then what's left over is going to be some oxide. And then they've got some more things about oxoacids and ammonium compounds, but basically, if you have a decomposition reaction, either things split up into the individual elements, or what happens is in reality, what these things are showing you is small, stable molecules come off. Okay, so things like if something can split apart and form something like water, H2O or water molecules are very stable. And so it can be favorable for something to split apart and release that very stable compound. Or carbon dioxide is also a very stable compound. So that tends to come off of things. Or ammonia and H3, that's a very stable small molecule. And so that can decompose off of things. And so this table just provides you a resource of some general common types of decomposition reactions when it's not just splitting up definitely into the elements, which is trickier to predict. And so you have to go off of just general characteristics of these types of compounds to figure it out. Okay. But in general decomposition, your first thought should be, I have this substance and it splits up into the elements. Okay, that should be your initial thought. But when you have carbonates, or you have, say, hydroxides, or you have ammonium compounds, those tend to form the small, stable carbon dioxide, water, ammonia molecules. Okay, so let's just look at a few examples. We want to predict the products of these decomposition reactions, okay? And even if I didn't say it was a decomposition reaction, if I said predict the products of these reactions and you're just given one reactant, the only thing that could be happening is a decomposition, okay? So there being only one reactant, that's a big hint. Now, the first one's just magnesium oxide, so it's only got magnesium and oxygen. So the only thing that can happen is it split up into the elements. Okay, we can't form new compounds from that, okay, because it's already a small compound. And so my two elements are magnesium and oxygen. And then we just have to think about when magnesium's by itself, it's monatomic, so it's just one magnesium atom, and it's a metal, so it's going to be solid, okay? And then oxygen, when that's by itself, it actually always is going to be diatomic, so O2, and that is a gas when it's by itself. Okay, and so those are our products. And then if we want to balance the reaction, even though I didn't say here to balance the reaction, let's just go ahead and do that. Here we have one magnesium on each side, but we have two oxygens on the right, so I need two of those magnesium oxides, meaning I need two magnesiums. So that would be my balanced reaction that actually occurs. Now the next one, I've got PbCl4 solid decomposing. Again, this is only made up of two elements. So the only thing that could happen is it split into those two elements. So it's going to split up into lead and chlorine. And so then I have to think about, how do these exist by themselves? Well, lead's a metal, so it exists as individual atoms. So it is just Pb, and it's a metal, so it's a solid. And then Cl is one of our diatomics, so it's Cl2. And chlorine, if you look it up, it is normally going to be a gas, okay, just like oxygen's a gas. And so that would be our products, is solid lead and chlorine gas, okay? And if we balance that reaction, we would need two of those Cl2s. Now the last one, we've got zinc carbonate, okay? And zinc carbonate, that's got three elements. So you could have a complete decomposition into zinc, carbon, and oxygen, but generally larger molecules are going to first decompose into just smaller molecules. And in this case, what you should key in on is you have a carbonate. And so carbonate, within that, you could kind of split off a CO2. And CO2 is a really stable small molecule, So that's what's going to happen. And you can even see that if you go back to that table. Remember, it tells you metal carbonates decompose to a metal oxide and carbon dioxide gas. Okay, so the metal still stays bound to oxygen, and then carbon dioxide comes off. So we're going to have zinc with oxygen, and then we're going to have carbon dioxide. Okay, now with that, you've got to be a little bit careful because the metal oxide, it's not necessarily 1-to-1. Okay, in this case it is, because when zinc is an ion, it's Zn2 plus and oxygen's O2 minus. So those do combine 1-to-1. Okay, but if that was forming some other charge, then it wouldn't. So let's say, for instance, let's do a different one. If we had aluminum carbonate, that is this. And so this would break into aluminum oxide, okay, and carbon dioxide. But aluminum oxide is not ALO. Okay, aluminum oxide is made up of Al3 plus and O2 minus. Oops, O2 minus, not a subscript of 2. And so we actually would need 2 aluminums and 3 oxygens for that aluminum oxide. And so you do have to be a little bit careful when you're doing this. Make sure if you're creating some ionic compound that the charges make sense. The charges balance to a neutral compound. Okay, so in this one, the zinc carbonate breakdown, that actually is balanced as is, whereas the aluminum oxide, this one, it would have looked like it wasn't balanced if you thought the product was ALO, but it's not. It's Al2O3. And let's see, is it balanced then? No, it's not, because you need 3 CO2s, right? You've got 3 CO2s, and so then now it's balanced. Okay, so that's the general idea of what a decomposition reaction is, kind of how you go about predicting products. You should at least be able to kind of break something down into the elements. So predict products of a complete decomposition. But realize when you have things like carbonates, something that can break off a small stable molecule like CO2 or NH3 or H2O, then that typically is what happens instead of it breaking into elements.